All right, let's get started. Hello, everyone. I hope you're all healthy and safe. Today, we will continue the SVM algorithm that we started last week. Okay, support vector machine or SVM. As I mentioned last week, it's a very effective algorithm. So we just started an introduction to the algorithm last week, and then we covered some a short review of linear algebra, mainly vectors and matrices that we needed for this topic and also for other topics that we will cover for the rest of the semester. Today we will continue and finish linear SVM. SVM, as you remember, it is a very popular and accurate machine learning algorithms. The algorithm is very simple but effective. SVM tries to find the best classifier. We call it hyperplane. It's a general term when we have n-dimensional space. But as I mentioned before, a 2D hyperplane is just a line, or a 3D hyperplane is a plane. So SVM tries to find the best hyperplanes, so these classifiers, or a group of them in our feature space, which can be used for classifying data samples. So this is what we talked about last week. A good separator or a good classifier, this black line is our linear classifier, can be a hyperplane that has the largest separation, or in other words, the largest distance to the nearest data samples of any class. So look in this picture, this sample is the closest sample to this line. So this is the nearest neighbor, in fact, and this is the closest distance. So if you find this distance and double it, this green area is called margin, okay? And so there's a kind of a safe zone where there is no sample in that, okay? So in support vector machine algorithm, in SVM, we are looking for the largest margin, okay? We are looking for the widest area among all of these classifiers. Each one of them give me a margin, right? So for example, for this purple one, this is the closest sample, so the margin is pretty, it's very narrow, right? This is the margin area. But for the black one, as you see here, the margin is wider, so it is a better classifier, because the samples that are close to the borderline are very risky samples. With a very small mistake or a very small change in one of these features, they will jump to the other side of the line. That is why we are looking for a classifier that gives us the widest area, the widest margin. This is the main idea of support vector machine algorithm. These so in SVM, we consider each one of these samples as a vector, okay? Each one of these samples will be one vector in this space, okay? And these samples that are on the border, they are called support vector. So this guy, for this classifier, this guy is support vector. Why do we call it support vector? Because this sample that are on the border, this one will help us find the best classifier. Okay, to find the best classifier, I just need these samples that are on the border. That is why we call them support vectors. And that's why we call this algorithm support vector machine. So I'm gonna explain it today. We are gonna start with a very simple approach, and then as always, this is my strategy. I always start with a very simple approach, and as we move forward, we make it more complex and more complex. Okay. Given a hyperplane like that, we calculate the distance between hyperplane and the nearest data point. If we double it, the area will called margin, and margin is the well, in fact, this green area is the area with no data sample in it. We would like to maximize this margin because the data samples near the decision boundary represent very uncertain classifier decisions and like risky samples. So the classifier with the largest margin probably is a very good reliable classifiers for classifying our data. So this is a completely new strategy compared to other methods that we have seen before. So in many of other machine learning classes, in machine learning algorithms, we define a loss function or a cost function, you remember that, and try to minimize these functions. Now we define another thing, margin, and we want to maximize it. So this is the idea of support vector machine, and previous results on real data have shown that it has been a very effective idea. So this is a classifier that we are looking for. Remember that this is still unknown. This is the nearest neighbor, okay, margin, safe zone, and we are looking for the widest margin. So margin is actually the area before hitting a data sample, okay? So this is the idea. This is not a good classifier. The margin is very narrow. So these samples, they are very risky samples. By making, for example, a small noise in humidity, these samples will jump on the other side of the classifier. All right. So now this is the main question: how to find the hyperplane, the classifier corresponding to the maximum margin. So let me talk a little bit about the general equation of a line, right? So in 2D, so again, I always start with a very simple case. So in 2D, when you have, for example, y and x, okay, well, an arbitrary line, the equation of that will be y equal to like ax plus b, right? So this is a general equation of any line, a 2D line. Well, in general, because we want to work with many features, let's call this like x1 and x2 rather than x and y, okay? So if I want to change it a little bit, so my new plane will be like x1 and x2, because in general I may have 100 of these features, and so I use indices to show them. And then this guy, I make this again a little bit more, let's generalize this equation and change it to something like that. I call it weight x1 plus weight 2 x2 plus some constant, whatever you want to call it, b equal to 0, okay? So this is actually the same thing. I just changed the name of variables to make it a general equation so that I can use it for an arbitrary number of features, okay? Here you go. Still, this is a line. It's a 2D line in this space, x1 and x2, okay? So in general, when you have m features, this will be your equation, okay? So if you have 3 features, for example, a third feature x3, 3, okay, then this is still linear, okay? So I will have a plane. When you have 3 features, this will be your classifier. When you have 4 features, of course I cannot show it on the paper, but when you have 4 features, again, you have a model in 4D space. But this is the general equation for a linear model in m-dimensional space. So now, again, like before, to make it simpler, I use the vectorized version of that. And because of these reasons, I needed to review vectors. So I put all of these weights into a vector, and all of those features into another vector. I call it W, I call this X. And if I want to make this equation, a vectorized version of that will be this, okay? W transpose means this vector, W1, W2, all the way to Wm times vector of X, all the way to Xm, okay? First row multiplied by first column, this one, okay? So this part is equal to this part. Okay, it's just compact version of the equation. Or equivalently, you can use dot product or inner product that I talked about this last week. Okay, so this is an equation for a line or a hyperplane, a linear hyperplane in m-dimensional space, or it's an equation for an m-dimensional linear hyperplane, okay? This one, in an arbitrary space. This is the equation. So we will work with this from now on. So here we go. In 2D, this is what we have. I use 2D because it's easier to show, okay? So I have 2 features, x1 and x2. This is the equation of my line that I want to find it, okay? So this is an unknown line. This is an unknown classifier that I'm looking for. So because it's unknown, so W and B are unknown. So I just need to find W and B. If I can find it, then I will find this line. So there is a very interesting thing. I'm sure most of you know this, but maybe you didn't really notice that. When you have a line like this, okay, so this is a line. Any point on the line, any point on this line, these samples, okay, they meet this condition. So if this is, for example, an x1 and x2, whatever it is, x1 and x2, if I put it here, this equation will be equal to 0, right? This is obvious. This is the equation of this line, so every point on that will follow this equation. It meets this equation. But anything on this side of the line, for example, above the line, if we put points here, if we put those points into the equation, okay, the value of the equation will be positive. On the other hand, anything on this side of the line, if we put these samples in the line, the value of this will be negative. Okay, this is important. So anything on the line, any point on the line, by point I mean data sample, right? This is our feature space. Anything on the line makes it 0. Anything on this side of the line make it positive. Anything on this side of the line make it negative. Okay, or vice versa. So let me show you an example. So these are 2 points right here, 2.44. If I put it here, it will be minus 3 times 4 will be minus 12, plus 2 times 4 will be 8, plus 4 will be 0. This one, 2, 1. Minus 3 times 2 will be minus 6, plus 2 plus 4 will be 0. Okay? But look at this guy right here. If I put it here, it will be minus 3 times 6 plus 2 times 3 plus 4, which will be minus 8. Okay, so it makes it negative. Here you go. If I put a value on this side of the line, if I put it here, it will be 8 positive. Okay. Why do we need this? Why this is important for us? Because this can let us know if one data sample is on left hand side of the line or right hand side of the line. So if this is one of your data points, one patient or one day or one stock market or anything you want to predict, if you put it here, make it positive, make the equation positive, it means that it's on the left hand side of the line, so you can predict sunny. If you put it here and it makes it negative, it means that it's on the right hand side of the line and you predict rainy. Okay, so this sign of this will tell you if one data point is on the left hand side of the line or right hand side of the line. In other words, it tells you if it is positive sample or negative sample. So there are 2 questions here, training and prediction. How can we use this idea to build a classifier? So prediction is very easy. I just mentioned that. Suppose that you have already this classifier. This is prediction, right? So it means that you already trained this. You already trained it, this classifier. So you have this line. A new data sample, a new point comes, and you put it here just to put this data point in the equation of the line. If it is positive, you predict it's on this side. You predict sunny. If it's negative, you predict rainy. That's it. So prediction is very simple. How about training? So I have a lot of data samples. Okay. In training stage, I have data samples. I want to find this line. Okay. This is the idea of training. How can we do that? So again, this is pretty straightforward, right? I have to find a line. So listen carefully. I have to find a line so that if I put positive samples of training in that line, the equations becomes positive. And if I put negative samples of my training sets in this equation, the equations becomes negative. Okay, if I'm looking for this, so if I do that and it works, it means that my classifier can classify those samples. Okay, so for any positive sample, if I put it here, this equation should be positive. For any negative sample, by negative I mean negative label, whatever it is. It can be rainy, for example, or it can be whatever you want to predict. It can be cat and dog. Okay, you want to detect if this is a cat or dog. If you put cat pixels as features in this equation, the equation will be positive. If you put dog's pixels, image of dog, in this equation, it will be negative. Okay, so the so far I'm just talking about binary classification, by the way. Later I will tell you how to expand it to non-binary, but for now let's focus on binary. So you have two labels. If I put one label, it makes it positive, other label makes it negative. This guarantees that all of the positive samples will be on one side of the line and negative samples will be on the other side of the line, so it will be a good classifier. So given a set of training data points, each point will be considered as an m-dimensional vector in the space. We are looking for a line whose value is positive for red samples and negative for blue samples. Okay, so this is clear. This is what I'm looking for. So your line should satisfy these conditions for your training data. So this is the first requirement for your classifier to work, right? So let me see how we can even make it better. Rather than one single line, I want to find an area that meets this condition, okay? So to do that, I define two lines in parallel with the original line. So this was my original line. I shifted a little bit to the left. I create another line which is in parallel but a little bit to the left. To do that, I would say this equation, rather than equal to 0, I would say it would be equal to 1. Okay, so this one doesn't matter what it is. Okay, it's just an arbitrary number that guarantees that this second line will be a little to the left of the first line. Okay, and similarly this line will be a little bit to the right of the original line. So I define two lines, one on the left, one on the right. And now rather than using this gray line for our classification, I want everything. So I take one further step. I want every data point. So this is an area that I just defined. By defining these two lines, I define an area. Okay, this is a gap. Okay, so now I want everything, every data samples which is positive, to be on the left hand side of this area, the whole area, this gap. And any blue sample will be on the right side of this gap. Okay, so it is like, rather than having a single line, I will have a wide area as my classifier, a gap, like a band, as my classifier. So let's do even better. We can find two parallel lines rather than just one line that separate the two classes of data. So to do that, red samples should be on the left hand side of this line now, and blue samples should be on the right hand side of this line now. Okay, these are my two equations. All right, now let's do even better than better. For SVM, let's find the two parallel lines that separate the two classes, as I mentioned, and the distance between these two lines are as large as possible. So I have these two lines that meets this condition, but also I want them to be as far as possible. So this distance between these two parallel lines should be as large as possible. Okay, so now I have, this is my first line, this is my second line. Every blue sample should meet this to make sure that all blue samples on the right hand side of the second line All red ones should meet this condition to make sure that all red samples are on the left hand side of the first line. And one more condition, I am looking for the two lines that are as the distance between them is as large as possible. It's actually the maximum margin that I talked about. Okay, so this is what I want. Using these conditions, I can find my SVM classifier or largest margin. Okay, so this is our problem. This is what we want for every data sample. If this is the condition, so look, I don't compare with 0 anymore. I compare with 1 because this is a line which is a little bit to the left. If this is the rule, I predict 1. If this is what happens, then I predict -1. So this is my prediction. So now I have this line and that line. So remember that W and B are the same things, okay? W and B's are the same. So if I find W and B for one of these lines, then I will have, for example, for this red one, then I have this one too. Okay, these are just a little bit shift of the original one to the left and right. So M is my margin, which is the distance between these blue and red. This is the equation for red, this is in blue. It is possible, here you go, I put the proof here, but it's optional, just for you. If you are interested, I can prove it here that the distance between these two lines are equal to 2 divided by norm or length of this W. Okay, now formulation. I want every positive sample be on this side of the red line. In other words, I want every positive samples meets this equation. So for every positive sample, if I put the features in this equation, it should be greater than 1. For every negative sample, negative samples, label, if I put the features in this equation, it should be less than -1. Okay, and at the same time, this M, which is the area between them, should be as wide as possible. So now, based on that, I can define a new optimization problem. I want to maximize this, which is M, such that for positive Y's, for positive samples, positive labels, this is the rule. For negative samples, this is the rule. Okay, so this is my new optimization problem that I have to solve. And so remember, for our problems, okay, as soon as you find an equation like this, an optimization problem like this, as long as it's a convex optimization, I'm going to talk about this in a minute, then we are done. Okay, so now we are good. We don't care how to, I'm briefly explain that, but as a machine learning person or as a computer science person, when you form an equation like this, okay, a convex optimization problem, we can solve it, so we don't worry about it. Okay, so mathematicians can solve this problem for us. You just need to define this equation, so this optimization problem, okay, and your mathematicians can solve this problem for us, so we don't worry about it. So again, we want to maximize this margin. Okay, this is what we wanted for SVM, such that all of the positive samples are on this side, all of the negative samples are on this side. So this guarantees that the classification works, and this guarantees that it is largest margin classifier. In other words, it's an SVM. So let's continue. Let's simplify this formulation a little bit. First of all, so we don't worry that much about solving this problem. I just want to make it a little bit more compact. First of all, maximizing, making this maximum is equivalent to making this minimum, right? So I just reverse that. I just reverse this. So in fact, maximizing this, it is equivalent to minimizing this denominator. So this is equivalent to this. All right. So this is the first thing. And I made it a squared because we want to make it convex. So by convex, let me tell you something. These problems are called convex optimization. It means that your function that you want to find the minimum of that, for example, it's like this. It's like a ball shape. This function is called convex. So because it's convex, it has a global minimum that we can find. Okay, definitely. So there are many different techniques to do that. So for example, in artificial neural networks or linear logistic regression, we used gradient descent. For this problem, we are going to use Lagrange multipliers, but it's all optional. I'm not going to talk about all details. The only important thing that you need to know is that it is a convex function, and there is a minimum for that, and we can find it. So as soon as you develop these equations, as soon as we know that it's a convex function, then we can find the minimum of that. So when by making a square, make it quadratic, it guarantees that it's like a convex function. So this is the first change I make. And secondly, I want to simplify these two rules. So you remember I said here you go, I have it. When y is 1, this should be greater than 1. When it's -1, this should be less than -1. So I want to combine these two into one equation. And I claim that this is equivalent to two of them together. This one alone, when I multiply y by this. Because if this guy, the label, is 1, then this equation will be wtx plus b greater than or equal to 1, which is this guy. Okay, when this one is -1, so we will have negative wtx plus b greater than +1. If you multiply both sides to -1, then wt x plus b will be less than or equal to -1. Okay, which is this. All right, so this equation alone, it is equivalent to two of these conditions together. And I made this small change, so this will be your problem. Our optimization problem will be this. Again, it has two parts. This part guarantees that your classifier works. It means that for any samples which is positive or negative, if we put it here, it classifies it correctly. It's on the left hand side of the line or right hand side of the line. And this part guarantees that you will get the widest margin, which is SVM classifier.